My name is Abby Rose, and today we'll be discussing the chemical compound ibuprofen. More commonly known as Motrin or Advil, most people know ibuprofen as the pill you take when you're in pain or suffering from a fever. I know ibuprofen quite well, as I have to take it every once in a while for chronic pain in my ankles and feet. But what is ibuprofen actually doing in your body, and how is it doing it? Those are a few of the questions we're going to discuss today. Now, here are some common examples of ibuprofen tablets and capsules. And just for some simple and general knowledge, ibuprofen usually comes in tablets or capsules that are 200 milligrams. The normal dosage for teenagers and adults is 400 milligrams every 4 to 6 hours. Ibuprofen can be harmful if it is taken on the daily, as it impacts and irritates the stomach lining, which can lead to stomach ulcers. Now, as for ibuprofen's properties, in its normal state, it is made up of small, clear crystals and has a melting point of 75 to 77 degrees Celsius. Ibuprofen is part of the non-steroidal anti-inflammatory ligands group, or NSAIDs. Other NSAIDs include naproxen, which is also a common medicine, found in Aleve, and also aspirin. Ibuprofen is also a non-selective inhibitor, meaning it has the ability to decrease a response in your body. In this case, the response that it decreases is pain or fever. Due to ibuprofen being made up of mostly non-polar bonds, which we'll be discussing in a moment, ibuprofen is insoluble in water, meaning that it doesn't dissolve. Looking more closely at the molecular structure of ibuprofen, we can see that it is a carbon chain with a benzene ring in the middle, as well as 2 oxygen atoms at the end with a hydrogen atom attached to one of them. In total, there are 13 carbons, 18 hydrogens, and 2 oxygens. Ibuprofen's unique structure gives it the chemical name of 2,4-isobutaphenyl propanoic acid. Due to its long carbon chain, ibuprofen is made up of mostly non-polar bonds, with the exception of the 2 oxygen atoms at the polar end. These polar oxygens are extremely important, and they allow for functions that will be discussed later. Ibuprofen is also a stereoisomer, meaning that the molecular formula mentioned earlier can have multiple different compositions and functions, while still containing 13 carbons, 18 hydrogens, and 2 oxygens. Now, here are some examples of ibuprofen stereoisomers. Looking more deeply at ibuprofen's stereochemistry, the drug is made up of a racemic mixture of its S and R enantiomers. This means that these 2 ibuprofen molecules are mirror images of each other, and they are non-superimposable, meaning that you can distinguish one from the other. Because they are mirror images, they have the same physical and chemical properties, which is why a mixture of both enantiomers will provide the same fever and pain relief as a solution of just one. And this is why the ibuprofen that you buy from the store is a mixture of both. Many people often wonder how ibuprofen knows where to go, or more specifically, what area of the body it needs to target. The truth is, ibuprofen doesn't know where to go, and instead is targeting the entire body. Prostaglandin is a lipid in the body that is produced in high amounts when the body is dealing with an illness or an injury. Prostaglandin specifically works on nerve endings by making them very sensitive, which tells the body that something is wrong. These nerve endings produce pain, inflammation, or fever. Prostaglandin is produced by a group of enzymes known as cyclooxygenases, one of which is COX-2, which we'll be focusing on in this video. Ibuprofen is able to stop COX-2 from producing prostaglandin, which means that there is nothing acting on the body's nerve endings, thus the decrease in symptoms you feel when you take the pill. As mentioned earlier, the oxygens on the polar end of ibuprofen's long carbon chain play a very important role in its function. Tier 355 is an amino acid, part of COX-2, again, one of the cyclooxygenases that produces prostaglandin. Due to the presence of the polar oxygens, a hydrogen bond is able to be formed between the carboxylate group in ibuprofen and the carboxylate group of tier 355. This is an example of that hydrogen bond. This bond stops COX-2 from oxygenating arachidonic acid, which is a crucial step in the production of prostaglandin. This makes the polar oxygens on ibuprofen extremely important, as they are the main factor to inhibiting the activity of COX-2, which stops the synthesis of prostaglandin and stops the pain and fever within the body. Previously described, ibuprofen is insoluble in water. So how is it able to dissolve in the body? Modern ibuprofen capsules and tablets are covered in a polymer called enteric coating. You may see it if you get water or a liquid on a pill. You'll see a color kind of rub off on the pill. This is that enteric coating. This coating does not dissolve in stomach acids and instead is able to dissolve in the small intestine. Releasing the medicine in the small intestine instead of the stomach helps it to reach the bloodstream quicker, which makes it more effective and means you can increase the time taken between doses. These are some pictures of some common forms of ibuprofen that use enteric coating. We have tablets and capsules. There are multiple ways companies mass produce ibuprofen for sale, but today we'll be focusing on a process used by students in organic chemistry labs like the one I'm in. The process starts off with reactants isobutylbenzene and acetic anhydride, which, by using Friedel-Crafts acylation, form p-isobutylacetophene. It is then reduced by NaBH4. The hydroxyl group is then replaced with chlorine and then reacts with magnesium to form a Grignard reagent. Carbon dioxide is then used to force a nucleophilic attack on the Grignard reagent, which gives you the ibuprofen we know and love. Thank you very much for watching, and I hope that you learned a little bit more about ibuprofen, its function, its properties, and its synthesis. These are the references that I used to make this presentation.